All right, here we are with section 4.4 on the fundamental theorem of calculus. Now that we've done area all the fun ways, including geometric shapes, Riemann sums, and that really lovely limit definition, there is a simpler way to find the area under a curve, and that is, so if we're on an interval from a to b of f of x dx. To find the area, we take the antiderivative, capital F, and then we plug in the top number b and subtract the antiderivative of the bottom number a. That is it. This can also be written as f of x from a to b, and this is the notation that I'm going to use. As soon as I take the antiderivative, we're going to have this vertical line to remind us to plug in a and b if it's a definite integral. Okay, so let's evaluate this. X squared minus 3 from 1 to 2. The antiderivative of that is x to the third over 3 minus 3x, and we're evaluating that from 1 to 2. So the long way here would be to plug 2 in to both terms in the antiderivative, and then we plug 1 in to both terms on the antiderivative. And then simplify that. That's negative 2/3. So we certainly could have done that the long way, the antiderivative way, um, or the Riemann sum way with the limit definition. It would not have been that fast, that's for sure. So this is a really nice tool to make things go a little faster. Very fundamental, if you will, fundamental theorem. All right, next one. So we have 3 times x to the 1/2. Let's just rewrite it like that so you remember that the square root of x is the same thing as x to the 1/2. You can pull that 3 out if it makes you uncomfortable being next to the x to the 1/3, but I'm just going to leave it out and then multiply by the antiderivative of x to the 1/2, which is x to the 3/2 divided by 3/2. And we're evaluating that from 1 to 4. So notice I haven't had the plus c. So we do not put the plus c if it is a definite integral. We evaluate it from those two numbers, but we do not plug in the plus c. Okay, so if I was to multiply by the reciprocal here, the 3's cancel. So it's 3 or 2x to the 3/2 from 1 to 4. So first we plug the top number in, 2 times 4 to the 3/2 minus 2 times 1 to the 3/2, which is 14. Okay, now we're getting into functions that we couldn't have even done using the Riemann sum limit definition because it's a trigonometric function, and that we didn't learn how to do any of those. We just had simple polynomials. We probably couldn't have done b either with the radicals, so let alone c. So the antiderivative of secant squared, let's think about what function would I take the derivative of to get to secant squared, and that is tangent. So remember, you can always do that if you can't remember. From 0 to pi over 4. So first we plug in the pi over 4 and the 0. So we should be able to know what this is off of our heads because memorizing the unit circle is pretty key actually. So tangent of pi over 4, at pi over 4 sine and cosine are the same at square root of 2 over 2, which means tangent is 1. And at 0, the point is 1, 0. So then to divide sine over cosine, it would be 0 over 1. So this tangent of 0 is 0, and my entire answer is 1. Great, that is much better. Okay, so now we're going to do an absolute value. Let me get my calculator out here. So we can see what this looks like and where it changes direction. Because remember, when we have an absolute value function, we need to find out where that term is so we can turn this into two separate integrals. We cannot do it as one. The absolute value of 2x minus 1. It changes direction at 1/2, and we're going from 0 to 2. so we want to find this area and this area. So I need to first set this up as, I'm going to show you what the piecewise function would be and where it changes direction. So really this is the opposite of 2x minus 1 when x is less than 1/2, and 2x minus 1 when x is greater than or equal to 1/2. It doesn't matter where you put the equals. You could have put it with the first one as long as you don't have it on both. Okay, so now we're going to turn this into a two separate integral problem. The first one is from 0 to 1/2 because that's where it changes direction, and the function, as you could see, was the opposite of 2x minus 1 dx, and then we're going to add the integral from 1/2 to 2 of 2x minus 1 dx. So now we're going to do the antiderivatives. This is going to be negative x squared plus x. We're evaluating that from 0 to 1/2, and x squared minus x. It makes sense that those are opposite integrals then. 1/2 to 2. Okay. So I'm going to show the work of plugging in the numbers because this is still new. But as we go, I am probably just going to go from the vertical line to the answer, understanding that we're just plugging in the top number and plugging in the bottom number. So first we're going to plug in the top number of the first question, the first integral, and the second one is just 0, plus plugging in 2 minus plugging in 1/2. Okay, and obviously you would use your calculator to simplify unless you wanted to do a lot of fraction work in your head or on paper, and the answer is 5/2. I mean, you could have also looked at this and saw that they were triangles and done the area formula for triangles if you wanted to. It would have worked just fine. Okay. On this one, however, since it's a parabola, there's not going to be any sort of geometric formula you can fall back on. This one you have to do the fundamental theorem. So we have the area bounded by the graph of 2x squared minus 3x plus 2, the x-axis, and the vertical lines from 0 to 2, as shown. So how about we show that so we can get a visual. 2x squared, whoops, might want an x there, minus 3x plus 2. We're going from 0 to 2. So we're picturing this little area right here underneath the parabola. Looks like it would be about here. So we just need to set up the integral and do the antiderivative and plug in our top and lower bounds. So if it's from 0 to 2, those are our bounds in terms of x. 2x squared minus 3x plus 2 dx. Take the antiderivative of that. 2 times x cubed over 3 minus 3 times x squared over 2 plus 2x evaluated from 0 to 2. In times like these where you see that every single term has an x in it and one of your bounds is 0, you really only have to plug in the other one. So here we're only plugging in, we're only plugging in the 2. When we do that, we get 10/3 is the area of that curve there. Okay, so the mean value theorem for integrals, I know for derivatives it was pretty important. We did a lot with it, but we are not going to do a lot with it for integrals. I'm just going to tell you what it is. We have a continuous function on the closed interval from a to b. There is some number c in the closed interval such that you can take for the antiderivative for the integral from a to b, f of c times b minus a gives you the same value as the integral. Are we going to use that ever? Probably not. So we will, however, be using the average value of a function. This is relevant and used quite frequently. You will be asked to find the average value of f, and you have to know this formula. You can't, they don't give it to you. So we take the, on the outside of the integral, we do 1 over the difference in the interval b minus a times the integral. So as long as you remember that 1 over b minus a on the outside, this is really not that vastly different, but we do need to remember it for average value problems. So it's always going to say in the question to find the average value, to remind you to do 1 over b minus a out front of the integral. So we would just find the antiderivative as normal, and we're just going to multiply our answer by 1/3. Pretty straightforward. So this is going to be x cubed for the antiderivative and x squared. We're evaluating it from 1 to 4. So first, if we plug 4 in, and then plug 1 in. And we should get 48 inside of my brackets, but since we have to divide by 3 on the outside, the answer is 16. All right, next we have a piecewise function that represents the different altitudes of the Earth's atmosphere and the different speeds at which sound travels at those atmospheres. So each one is represented by a piece of the piecewise function and then described in terms of x, where those functions apply, where x is altitude. Oop, that should be here. Where x is altitude. There's no question either, might want that. What is the average speed? From 0 to 80. So now that we have a goal, now that we have a question, we are going to have to break, it's already broken up into the intervals for us. We just have to do all of the separate integrals, which looks like a pain in the butt. So from 0 to 11.5, our function is negative 4x plus 341. Luckily for us, these are all polynomials. These are all nice antiderivatives. This one turns into negative 2x squared plus 341x from 0 to 11.5. And again, to save us just a little bit of time, I'm not going to plug it in and show you. I'm just going to give you the answer for each individual piece of this. So that's 3,657 for the first piece. Second piece, from 11.5 to 22. It's just 295 dx, which turns into 295x from 11.5 to 22, which is 3097.5. Third piece, from 22 to 32, 3/4 x plus 278.5 dx turns into 3/8 x squared plus 278.5x evaluated from 22 to 32. 2987.5. Fourth piece, from 32 to 50, 3/2 x plus 254.5 dx turns into 3/4 x squared plus 254.5x from 32 to 50 is 5688. And one more piece to bring us all around here. From 50 to 80, negative 3/2 x plus 404.5 dx equals negative 3/4 x squared plus 404.5 x evaluated from 50 to 80 is 9210. So if I wanted to find the integral from 0 to 80, I would add up all 5 of my pieces. The question, however, is what is the average value from 0 to 80? So not only do I need to add them all up, but I also need to divide on the outside by 1 over b minus a, or multiply by 1 over b minus a. So first, the integral from 0 to 80 would be the sum of all the pieces, which is 24,640. So to find the average speed, I do 1 over 80 minus 0 of the integral, which is 308. And this is speed, so meters per second. Okay. So this is a antiderivative question with different values of x to plug in. So first of all, I would like to find out what the antiderivative is from 0 to x of cosine t dt. The antiderivative of cosine is sine. So this would be sine t from 0 to x. If I plug in the top, sine of x, plug in the bottom, sine 0. So this whole thing is actually just sine x. So now for the different values of x, I would just have to plug in those x values. At x equals 0, f of 0 would be sine of 0, which is 0. At pi over 6, f of pi over 6, again, I would expect you to have the unit circle memorized, at least the first quadrant to help you out. Sine of pi over 6 is 1/2. Pi over 4, sine of pi over 4 is, I mentioned this one earlier, square root of 2 over 2. Pi over 3, sine of pi over 3 is square root of 3 over 2. And last one, pi over 2 the height or the sine value or the y value at pi over 2 is 1. So I think we're actually going to stop the video there. There's going to be a part 2 that's going to start at the second fundamental theorem of calculus. I don't want the one video to get too horribly long. So we're going to stop there. Look for the second part of section 4.4.